welcome back to Online Statistics. Today we are going to talk about correlation. I'll give you an overview of correlation and then I'll give you a brief introduction to regression. First, we'll talk about the logic behind correlation. We will talk about the variable types that we use the correlation procedure for. We'll look at scatter plots and R values and the relationship between R values and scatter plots and how scatter plots are the graphs used to visualize a correlation. And then we'll talk a little bit about correlation and causation. I have a kind of a funny example I'll give you about correlation and causation. If you've ever taken intro psych, you should know that correlation does not necessarily mean causation. So you want to be careful with the conclusions you draw from a correlation. After that, we'll talk about the assumptions of the correlation, what needs to be met before you can run the correlation, the assumptions that have to be met with your data set, the things that the test is based on, and they're a little bit different than the assumptions you know this far. Then we'll talk about calculating Pearson's R. R is the test statistic for correlation. And we'll look at regression and how regression is related to correlation and how we use this correlation coefficient to then make predictions. And we use regression lines to create predictions for one variable based on the other. All right, so first a little background. The variable types that a correlation is used for are two continuous variables. So with a correlation, we're testing whether there's a relationship between two continuous variables. For example, is there a relationship between how many hours you study for an exam and your grade on the exam? Both of those variables, hours studying for exam and grade on the exam, are continuous. And so we want to know, is there a relationship between these two continuous variables? So it's a little bit different here. We're asking about a relationship, not a difference between groups like we were with ANOVA or t-test. We're asking about a relationship between two continuous variables. Now, Carl Pearson, he actually was the person, he lived in London, and he was the person who figured out all of the formulas. That's why many times we call the test statistic for correlation, we call it a Pearson's R. Pearson's R because Pearson was the one who worked through all of these formulas. But he actually gave the credit to Sir Francis Galton. He worked for him. So he was working for Galton at the time, and Galton was doing research on eugenics, and does he remind you of anyone? Look at his picture. Anyone look like anyone you know? He was actually Darwin's half cousin. And there was a lot of criticism that Pearson got and Galton for creating these statistics and using them for eugenics because they said it later may have been misused, even though that probably wasn't their original intent. So let's take a look at the logic behind this. So here are two continuous variables. We have hours of sleep and happy mood. They're both continuous. Hours you slept, you could sleep 4 hours, you could sleep 4.2 hours. And I want to know, is there a relationship between hours slept and how happy you are? So this is what you would test with a correlation. Now the way we represent correlation or two continuous variables and the relationship between those variables is by use of scatter plots. And here's an example of a scatter plot where each dot represents only one individual. So one individual's observation on two different variables. And so what you would do is you'd take this one individual, you'd ask them how many hours they slept, and you would go on the x-axis, go to however many hours they slept, and then you would have them take a test or a survey of how happy they are, and you go up and put a dot right where, up on the y-axis and x-axis that represents their position on two different things. So that one dot represents one individual, but their position on the variable on the x-axis, how many hours they slept, and the variable on the y-axis, how happy they are. So then you go and get the next person and plot their dot, and eventually you end up with a bunch of dots, and it gives you kind of a relationship between these two variables, the variable on the x-axis and the y-axis. You can see eventually this is what your scatter plot would look like. Now, the test statistic, R values, I'm just going to give you an idea of what R values are. They range from -1 to +1. And a zero, Pearson's R of 0 means that there's no relationship between the two variables. So the further you get away from 0, the stronger the relationship between the two variables. A -1 is a perfect inverse relationship. So an inverse relationship means that as one variable goes up, the other goes down. Or if that variable goes down, the other one goes up. There's an inverse relationship between the two variables. So for example, a negative relationship between the number of hours you sleep and how happy you are would mean that increase in number of hours you sleep, the more you sleep, the less happy you are. That would be maybe people who are depressed sleep more. And so there's an inverse relationship. They're less happy, they sleep more. They're more happy, they sleep less. So that would be a negative relationship. If it was perfect, it'd be -1, the relationship between the two variables. A perfect positive relationship is a relationship where both variables move in the same direction. So for example, if the more hours you sleep, the happier you are. They're both of those variables are going in the same direction. The less hours, fewer hours you sleep, you're less happy. They're both going in the same direction. There's a relationship, but it's in the same direction, and that's what we call a positive relationship. And a +1 for an R value is a perfect positive relationship. So it's a perfect relationship between these two variables. So if you think about R this way, the further you get away from 0, closer to either -1 or +1, the stronger the relationship between these two continuous variables. The negative or the positive tells you the direction of the relationship, whether it's an inverse direction or the same direction of those two variables. So here's an example using both the scatter plot and R value. You can see age of husband on the x-axis and then age of wife on the y-axis. And there's a positive correlation between these two. And this is what a positive correlation looks like on a scatter plot. It goes this direction, so it goes up. The positive correlation shows that as husband's age rises, so if you know someone's age, if he's older, the wife tends to be older. If he's younger, the wife tends to be younger. Now you notice there's some scatter around. It's not a perfect relationship. So here the correlation coefficient, R, Pearson's R, is 0.92. It's a pretty strong relationship, but it's not perfect. And the reason it's not perfect is because just because you know the husband's age doesn't give you the exact wife's age, but it does give you a range. It tells you she's probably between this age and this age, because if you look at the scatter around that graph. Now, a perfect positive relationship would look like the second graph, where the line is perfect here. So you see, on this line, R equals 1 +1. And if you know the husband's age, if this was the relationship between husband's age and wife's age, if you knew the husband's age, you would know the wife's age because the line has no scatter around it. So that scatter that you see around the line in this first graph, the scatter is error. It's error from our relationship between the variables. And the closer that is to a straight line like this, the stronger the relationship, the closer to 1 you would get with your R, your correlation coefficient. Here's another example of a positive correlation. Hours studied for an exam and grade on the exam. It's not a perfect relationship, but it looks like the more someone studied, the higher their score was on the exam. The less they studied, the lower their score on the exam. Now here's an example of a negative relationship. We have percent fat on the x-axis and fitness on the y-axis. Now, as your percentage of fat goes up, so remember, each of these dots represents one individual. So one individual with a high percentage of fat, high over here on this end of the x-axis, has a lower score on this test of fitness. Someone with a lower, this individual had a lower measure of percentage of body fat and a higher score on their test of fitness. Now, it's not perfect. There's some error around here. There might be people in this middle range who have high or low fat but aren't fit or are fit. But this is a negative relationship. As one thing goes up, as body fat goes up, fitness goes down. As body fat goes down, fitness goes up. And here this correlation is 0.79. So there's still a relationship. The relationship R is still closer to 1 than it is to 0, the relationship is closer to -1 than it is to 0 because it's a negative relationship. So you see here with this R, it's a negative value that represents the negative relationship between those two values. And you see on the scatter plot, it takes on a different slope. And over here, we have the perfect negative relationship, the line that follows the perfect pattern here. If this was percent of body fat and fitness. If you knew someone's body fat, you would know their exact fitness. We rarely in real life get this perfect +1 or -1 relationship, just because we have error even in things that have a perfect relationship with each other. Typically we don't have things that, two relationships are perfectly related. There are other things that influence them. And we have error influence. When we get a sample, there's always going to be error. So we typically don't get a +1 or -1 when we're doing real research, but those are the ranges that R can take on. All right, so the scatter plot shows no relationship. If you know this variable X, it tells you nothing about the variable Y, because there is no trend in the data. So if someone scores high on X, you have a whole range of scores for Y they could have. Or if they score low on X, it's a whole range of scores they could get on Y. So there's no relationship, and no relationship between two continuous variables is represented by an R value, Pearson's R of 0. But like I told you, we never get a +1 or a -1 when doing real research. So you probably aren't going to get a perfect 0 when you calculate R either. So I say no relationship is 0 or close to 0. So the question is, how close do you have to be to 0 to say there's no relationship, or how far away from 0, how close to -1 and +1 do you have to get to decide there is a relationship between the two variables? Now you should be thinking, oh, this is probably based on sample size, because with a smaller sample, you have more room for error. A larger sample, less room for errors. And yes, it is going to be based on sample size. It's also going to be based on a formula that calculates how much each score changes in this trend, how much X changes with Y, how much Y changes with X. So we're going to do significance testing with a correlation with R, just like we have all the other statistics. First, we ask, what is the relationship? Then we ask, is that relationship strong enough, or is it significant? Is it not likely we would get that strong of a relationship by chance? And we decide whether to retain the null or reject the null. Now the null hypothesis here, no relationship between the two variables. The alternative hypothesis is that yes, there is a relationship between the two variables. So if you have enough evidence that gets you far enough away from 0 with your R value, then you go to your significance table just like before. I'll go to that in a minute. You're going to reject the null, go with your alternative hypothesis that there is a relationship between the variables. All right, so let's talk a minute about correlation and causation. Now, just because two things are related does not necessarily mean one causes the other. So what if I was to tell you that there's a positive correlation between foot size and IQ? Okay. What would you think? I want you guys to think about this. But pause the video, go and post a few comments. Tell me what you think about this. I'm not lying to you. There is a positive correlation between foot size and IQ. So what does that mean? That means that as foot size goes up, this foot gets bigger, IQ also goes up. Smaller feet, smaller IQ. Positive relationship like this. Okay, so this is true. So give me some feedback on what you think about this. All right, I'm going to go to the drawing board for a second. And I'm going to draw the relationship between foot size and IQ. So we have an x-axis here and a y-axis here. And the relationship looks something like this. Okay. So here you can see as foot size increases, so does IQ. Okay. Now it's not a perfect relationship. There's still some room for error. If you know someone's foot size right here, you know that their IQ is probably between this range. If you know their foot size down here, you know their IQ is between this range. But there is this positive relationship between these two continuous variables. Now, does that mean that having large feet causes you to be smart? What do you think? Perhaps. What about having a high IQ? Could it be that if you're smart, you eat good food and that makes you grow and have large feet? Possible? Can anyone think of a different explanation for this relationship between these two variables? Can you think of anything? Think about it for a minute. So, what about age? I didn't say anything about age. I'm not measuring age here. And in fact, if you control for age, so if you think about it, who has the smallest feet? Who has the smallest feet? Babies. Okay. So here are the babies. And yes, babies perform worse on IQ than children who have the next smallest feet, or adults up here. And so now if you think about this third variable, a variable that we didn't even measure, we didn't look at, that you go, aha, that no wonder there's a correlation between foot size and IQ. There is a relationship between these two variables, but it's explained by a different cause. Aging causes your foot to grow bigger. Your brain develops, you get smarter as you go along and you age. And you're better at performing tests, taking paper and pencil tests. Babies, have a really hard time with those types of things. So if you look at these things individual, is there a relationship within age? No relationship. They look like those scatter plots I showed you before, where there's zero correlation or close to zero correlation. So my conclusion here is that no, having big feet does not cause you to be smarter, and they are related, but there isn't a causal effect here. So you need to be careful when you see that there's a correlation or a relationship between two variables. You need to be careful about the conclusions you draw based on the significant correlation. Just because there's a relationship doesn't mean one variable causes the other. So here is an example back at the PowerPoint of how there can be relationships between variables. When you find a correlation, it could be that X causes Y. So in my example, it could have been that the foot size causes difference in IQ, or it could be that Y causes X. Maybe IQ causes differences in foot size, or it could be some third variable like Z that influences both at the same time, like age that influences both foot size and IQ. So you want to keep this in mind. A lot of times we like to draw conclusions that relationships between things mean that one thing causes the other, and you want to be careful not to do that. All right, so let's talk about the assumptions for correlation. They're a little bit different than the assumptions we've used for t-test, for ANOVA, but they're similar in some ways. So first of all, we have, with the type of correlation we're doing now, linear correlation, with bivariate linear correlation, bivariate two variables. We're not going to get into multiple regression correlation with more than two variables in this class. That's an advanced topic if you go on to study more statistics. But we do have to have a linear relationship between our two variables for the correlation to work. And so what I mean by linear is a straight line would fit the data best. So if you look at this graph, there's a curvilinear relationship. We have on the x-axis arousal. So arousal could be how much anxiety you have, whether it's very low, moderate, or high. And performance on a task. And they find that if you have a little bit of arousal, so you're alert and awake, that you perform well on the task, not if you're very low on the arousal where you're sleeping and having a hard time focusing and paying attention. But if it gets too high where you're really aroused and you're panicked, you're not going to perform well. So you end up with this curvilinear relationship, and this is not good for the linear correlation that we're doing. So first we have to meet the assumption that your two variables have a linear relationship with each other, that they create a line like we were looking at earlier. A couple of other assumptions of the correlation are normality of residuals and homoscedasticity. It's kind of a fun word to say. So remember the assumptions that we used for t-test, for ANOVA. Remember we had assumption of normality, but here we don't have a normality as a basic assumption. It's normality of the residuals. And let me draw an example of normality of the residuals because it's a little different than the normality you're used to. So normality no longer matters for each variable x or y, but it matters about the relationship between x and y. So if you were to make a scatter plot, the residual is how far each dot is. So most dots, are going to fall close to that line or far from it, depending on the strength of the relationship between the two variables. But the residual is how far each dot falls from a line that best fits the data, that fits down the center, essentially, best fits into the center of your scatter plot. And so if you have the assumption of normality of residuals met, it means that most of the residuals fall close to the line, just like the normal curve. And as you get further and further away from that line of best fit that fits in the center of your data, as you get further and further from that, you get fewer and fewer scores that fall in there, fewer and fewer dots. So essentially you create a normal curve around this line of best fit. Most of your dots in the center, fewer and fewer as you get away from it. That if the scatter around this line looks like this, then you've met the assumption of normality. If you had scatter that was mostly concentrated out here in the tails, far away from the line, and then fewer dots in the center, but that line fit in the center of the data, you would not have met the assumption of normality of the residuals because you don't have most of the data in the center and fewer further and further away. You have most of the data out here in the tails. And so think of it as normality, but normality of the relationship of X and Y. So that's the normality of the residuals. The next assumption is homoscedasticity. And homoscedasticity, you can think of it as a similar assumption of homogeneity of variance. But now we're not dealing with 2 groups or 3 groups or 4 groups. We're dealing with relationships. And so you can't test that the groups have equal variance, but you can test that there's equal variance of the scatter of the dots around that line of best fit, the line, that the scatter is equal all the way across that line. So let me go and draw you a line here, and here's our X and Y. And if a variable meets the assumption of homoscedasticity, then it will be approximately spread equally. So the spread, you can think of this as standard deviation or spread, is similar all the way across the line. Okay? If this happens, then you've met the assumption of homoscedasticity. I'll draw you an example of a data set that would violate homoscedasticity. If you have a variable X and 2 variables X and Y, and let's say that there's a strong scatter around the line here, but as you get further out down this line, the scatter looks like this. So it's really spread out up here and less spread out here. That has not met the assumption of homoscedasticity. So you can think of it as HOV, similar to HOV, because the variance has to be the same, but not for 2 different groups or 3 different groups. It has to be the same across that line, or approximately same. So it's scedasticity, the scatter has to be similar across this line. Okay. So if you've met those assumptions for the test, then you can go ahead and use correlation. It's a good tool for you. And now calculating R, the main test statistic like T or F that you use in ANOVA, R is the test statistic that we use in a correlation. And calculating Pearson's R, basically you're looking at the relationship between X and Y. So you take this formula here, might look a little daunting, but it's not really. You're going to add up the relationships between X and Y. So what you do is you take each score, X. So let's look at the formula. X, that's the score of X, minus the mean of X. So first you have to take all of your variable X scores. So let's say it was hours that you studied was your variable X and the score on the exam was Y. So you would take hours studied, find the mean, and then take each score for hours studied, subtract it from the mean. Essentially, it's like a z-score. Subtract it from the mean, and then you take it and multiply it by the Y variable's z-score for that same individual, because remember that individual has 2 different scores on 2 different variables and we want to see how they're related. So you take then Y, that's all the scores on the exam, get the mean from those scores on the exam, and take that same person's Y score, subtract it from the mean of Y, and multiply it to the value you got from the distance from the mean of X. So you have the X score minus the mean of X multiplied by the Y score for that same individual minus the mean of Y. You multiply those together, and you do this for every single participant in the study, every single subject, every single observation. You multiply it, you get a bunch of covariance, so you're getting how these vary together, how X and Y vary together. You add them all up. Once you've added those all up, you know how much this X and Y varies together, but remember you still have to divide by some sort of error term. How much does it vary in terms of how far the variance is spread out? So you do divide by the square root of the sums of squared deviations, so of X, so how much the square deviations of X, and then the square deviations of all the Y scores from Y. And so here, just like all of the other stats you've learned, you have a relationship on the top. Now, typically we had a difference on the top. With ANOVA, we have a difference on the top. With t-tests, we have a difference on the top. Here we have a relationship or a covariance on the top divided by an error term on the bottom. So you're asking, what's the relationship? How strong is this relationship in terms of the spread of the error? Okay. Now, for calculating step-by-step correlations, go ahead and preview my PowerPoint that will walk you through how to calculate. I'll set up a table, or I have a table set up where you will see exactly what you're doing with x and the mean of x, y, and the mean of y in case you need a little bit more help getting through this. Okay. Now, once you've calculated r, you know what the relationship is, but you know that relationship, like I said, how close to it is it to -1 or +1 or away from 0? And so testing significance of r, you still have to do, because remember, we're still working with samples. There's still room for error. We have to decide, is this significant or is it not likely to happen by chance, this relationship with the sample size we have? And so you could introduce a new distribution of r values and the likelihood based on degrees of freedom, but instead we're going to just convert r to t, which is done very easily. You just take your r value and divide by, you first calculate the bottom portion, the denominator, the square root of 1 minus r squared, divided by n minus 2. That's your degrees of freedom. The number in your sample minus 2, you have to subtract 1 for x and 1 for y, because the x, once you know the mean, you have to take, there's only the n minus 1 degree of freedom to vary. Remember when we talked about degrees of freedom? And y, you have another mean where there are n minus 1 degrees of freedom. So you have 1 degree of freedom lost for x, 1 for y. And once you've calculated that, you just divide r by that value, and that gives you a t value. So it converts it to a t, and then you can use the good old t-test, the good old t-distribution. You can just use that for your significance level cutoffs to decide whether you're going to reject the null or retain the null. All right. Now, since r tells us the relationship between the two variables, it can also be used as an effect size. So a small effect is 0.10 up to 0.20, medium is 0.20 up to 0.50, and large is 0.50 or over. Now remember, I'm going positive in this direction. It also goes the same for the opposite direction, away from 0, negative. Okay, so a small negative correlation would be negative 0.10 or less than that to negative 0.30. I'm sorry, I don't know if I said 0.20 or 0.30, but it's 0.10, 0.30, and 0.50 for the effect size. All right, so now that you know all about correlation, an extension kind of correlation is the regression. Regression is where you use the relationship between x and y, this correlation coefficient, to make predictions if you know one variable. So if you know variable x, you can predict y. If you know someone's GPA score, you can predict how well they'll do in graduate school, perhaps. Or if you know their IQ, you might be able to predict their grade in a statistics class. And so it's taking one predictor variable, x, and then using that to predict your criterion variable, y. And in order to predict, you have to take that relationship with a scatter plot, put a line of best fit, and then make a formula or an equation to calculate that line, and that line, the formula for that line, the equation for that line becomes your formula to make predictions. So you end up using what we call a regression line and a regression equation to make predictions of y based on x. And this line of best fit you should be familiar with by now. It's just taking all of the points on your scatter plot and fitting a line into them so that you get the least amount of residual around that line. The least amount of residual, remember the least spread of those scatter around that line. So fitting it perfectly in there so you have the least amount of spread. And then that line, you end up figuring out what the equation is for that line. And then if you have a value of x, you just use that to predict y. And so here is the formula that we use for our regression equation. Y hat is just the predicted y value is a plus b of x. And a is our constant, so that's where the line crosses the y-axis. Wherever it crosses the y-axis, if it's at 0, it's 0. If it's above 0, then it's whatever value. The slope, the line of best fit, crosses the axis is a, and then plus b of x. And b is the slope, so it's the change in y that occurs with every unit of x, and multiplied by the score of x. So if you know the x score, you plug it in there, you use the slope plus the constant to get your predicted y value. And for exact calculations of regression, go ahead and refer to my PowerPoint that will lead you step by step through calculating these regression equations. Regression also has a different effect size. We use r squared as the effect size in regression, and it's just the sums of squares total divided by, or minus the sums of square error divided by the sums of square total. So essentially it's the proportion of variance explained in y by x. So it's how much variance in y, in variable y, is explained by variable x. And it translates to a percentage. So the percentage of variance in y that is explained by variable x. If you have any questions, let me know. It's been fun, and I can't wait to see you again next time.